Assalamualaikum.
We are from Galactic Geckos.
Today we will be presenting about related rates.
Before we get started, let's get to know us.
Oh.
And there's as well.
But before all that, let me talk about the history of differentiation. Newton and Leibniz essentially created integral and differential calculus. They were both interested in objects that are in motion. However, they both looked at different aspects of this. Newton was more involved with the speed of a falling object, and Leibniz with the slopes of curve to illustrate the rate of change. Although they both look at different things, they both came up with the same result. Hence, the accusation of stealing the other ideas. However, combining both of their ideas, fundamental theorem of calculus was created, which links the concept integration to derivation. So, what is a related rates? In differential calculus, related rates problem focus on finding how fast one quantity changes by linking it to other quantities with known rates of changes, usually over time. This approach is commonly used in science and engineering, where many quantities are interconnected. To solve this problem, we often need to apply the chain rule because they usually involve several variables. An example of related rates in real life is watching a bouncy ball being blown up or a plane moving through the sky.
Thank you, my friend Sharif, for explaining what related rates is. Today, we are going to present about a ladder problem. So, here is a picture of the problem that we are going to understand and solve. The ladder problem is a classic example of related rates problem in calculus. It typically involves a ladder leaning against a wall, where we analyze how the rates of change of various distance are related as the ladder slides up or down the wall. When the top of the ladder is pushed up the wall, the scenario and the related rates analysis are slightly different but follow similar principles.
First of all, let's analyze the given information. A ladder with length of 250 cm leans against a vertical wall. The top of the ladder is pushed up the wall 8 cm per second. Let's say we have x, which in this case, we make it as the distance from the bottom of the ladder to the wall, and y, the height of the ladder on the wall. We are going to find dy over dt, which is the rate at which the top of the ladder is pushed up the wall. dx over dt is negative 8. In this question, we will ask it to find how fast is to the top of the ladder moving up when the bottom of the ladder is 60 cm away from the wall. I will pass to Ikwan to explain how to solve this question.
So, for the calculation, to find dy dt, we need to first separate it. dy dt equals to dy dx times dx dt. We know that the value of dx dt, as mentioned before, is negative 8. But we do not know the value of dy dx. For the relationship, we are going to use the Pythagorean theorem for the right triangle that is formed by the ladder, the wall, and the ground, with the equation of x power of 2 plus y power of 2 equals to length power of 2. In this question, the length of ladder is 250. So, we can insert length in equation x power of 2 plus y power of 2 equals to length power of 2 and move x to the right and y to the left. So we can make it y equals to square root 250 square minus x square. After that, we differentiate to find dy dx and put the result into dy dt equation. After we got dy dt equals to dy dx times dx per dt, we put the value of x, which is 60 centimeter, into the equation. And after the calculation, the final answer will be 1.9778.
In conclusion, the ladder problem shows how calculus help us understand how changes in one part of a system affect another. By using related rates, we can determine how fast the bottom of a ladder move when the top move, or vice versa. This problem illustrates the concept of interconnected change in a clear and practical way.
Assalamualaikum.
We are from Galactic Geckos.
Today we will be presenting about related rates.
We get started, let's get to know us.
Before we get started,
Let's get
aduh, scroll.
Cuba bagi aku.
Assalamualaikum.
Gila. Apa? Aduh.